Alright, let's talk about some more electromagnetism. Electricity, gravity, magnetism, they are all fundamental forces, and we learned that back in Unit 2. Magnetism and electricity are closely related. They're generally regarded as two expressions of a single force, the electromagnetic force. So the first evidence of this relationship was by this guy Oersted, 1820. A wire that could carry an electric current was pointed north-south, so I'm going to try and draw this. So here is my wire, and we'll say that this is north. Okay. Before the current is switched on, I've got a compass here. Yes. And it's pointing north. Nothing's happening with this wire just yet. It's just near the wire. When current starts to flow through the wire, this needle suddenly no longer wanted to point in a northerly direction. It suddenly flipped and went that way if the current was flowing in that direction. So I'm going to point in a direction. We'll say, let's just say east-west direction. When the direction of the current flow is reversed, the compass needle, if suddenly the current was going this way, he found that the needle suddenly flipped and pointed in the other. Compass needle flipped around to point in the opposite direction, still at a right angle to the direction of current flow. This effect of current flow on a nearby magnet occurs because the moving electric charges that make up the current set up a magnetic field that curls around the wire. The direction of the magnetic field it's going to be expressed by a right hand rule, and we're going to be learning a few different right hand rules, and this is the first one. And I have a little diagram here to show you. Your thumb points in the direction of current, okay? And if you're watching right now and you're writing or you're not, put down your pen, get your right hand out and put it, maybe hold your pen like it's a wire, and then kind of like it's this wire right here, and then kind of gently grab it like this. Your thumb will point in the direction of current flow, and your fingers curl in the direction of the magnetic field. So there's a magnetic field going around this wire in this direction, from the positive to the negative terminal. Then the fingers of the right hand curl in the direction of the magnetic field. So this is your right hand rule. Anytime you're given a wire and the direction of current, you can figure out in what direction the magnetic field around that wire is going. And just to be clear, up here, of course, the Earth is still a giant magnet, and there's still a magnetic field around the Earth. It's just that this local magnetic field is so much more powerful to this compass than the Earth's magnetic field that it flips its direction. The principle of electromagnetism states that whenever an electric current moves through a conductor, a magnetic field is created in the region around the conductor. So if I look at a wire straight on, it's just a little, some little terminology here. If the current is going into the page, so here's my wire, and it's coming in and out of this page, and right now the current is going into the page, and when it's going into the page, the convention is to put an X here. So if I get my right hand out, and the current is going into the page, I'm going to point my thumb at this X. I'm going to point it into this page, and what direction will my fingers go? My fingers would be wrapping around like that. Yeah? Now, if the current is coming out of the page, we use a different symbol. We use a dot, and in that case, it would be the opposite way. The magnetic field would be wrapping around like that. So this is your little introduction to current, moving electrons, current, causing a magnetic field to be made, and then using a right-hand rule to determine in what direction that magnetic field is pointing.